Okay, so let's start our second week material. So far we talked about vectors and matrices, and the reason why we talked about such thing is that our focus is on the multivariable function. So multivariable function, let's say f of can be written as, in general, y1, y2, and so on. It should be finite dependent variable. Ym is given by f of x1 up to xn. But if we consider a tuple of real numbers as a vector, we can simply write the left hand side as a vector y and the inside of this right hand side as vector x. So we can rewrite this as f is a function sending n tuple of numbers to m tuple of numbers, which is a vector to vector. I didn't say this is a linear transformation yet, but it's just a function of vector to vector. And I didn't say that this vector has a vector sum yet, just saying that vector is an n tuple of real numbers. So that's why we talked about matrix vectors, and also matrix is an example of vectors, and there are other properties that we're going to use later for matrices when we talk about chain rule and differentiation. So from now on, let me give some other examples of vectors. So this is an old slide that I didn't change yet. So let me, I upload the updated version. So in the updated version, this slide comes first. So I will explain this one first. A function is called a multivariable if it consists of more than two independent or dependent variables. So in general, we can rewrite this multivariable function as sending n tuple of numbers to m tuple of numbers, where yj's, each yj is also already a multivariable function because each yj is determined by n tuple of numbers from x1 to xn. So this is also a multivariable function. So usually, because y represents a number, so we will also give another name, let's say fj instead of yj, but you can simply use yj stand for a variable or stand for name of a function. Okay. So when we talk about functions, the first thing that you have to think about is what's the graph. For example, if you have a single variable function, the graph is something like a curve inside of two-dimensional plane. But if you think about plane, if you think about curve in the plane, it's a parametric curve, right? So let's say we have y equals to f of x, a single variable function. Then the graph is nothing but a set of points lying on the curve inside of two-dimensional plane. So I can rewrite my graph of f to be a pair of points x, fx, where x lies in some interval. This is the domain of this function. Right? So I will just extend this definition. So whenever we have, for example, the simplest kind of multivariable function, which is the two-variable function, the graph of this two-variable function is set of points in three-dimensional space, consists of x, y, and fxy, where xy lies in the domain of function. So for example, let's say we have function f of this one. Let's look at this one first. Z equals to fx x squared minus y squared. So that's f of x, y. And let's assume that since we cannot draw this function entire plane, our domain of function is 0, minus 1 to 1, cross minus 1 to 1. So here is x axis and here is y axis. I can draw my point x comma y inside of xy plane, but I have another variable z, which is an independent variable, changing by the value of x and y simultaneously. So I need to draw another point. So that's why I need another axis, the z axis. And I first define my domain of function here. It looks like it's hovering over. So let me give a little bit more axis here. So let's say domain D lies here, and this is not the graph. This is simply the area of the domain inside of xy plane. What makes the graph is a set of points in three-dimensional space where so if I draw this, actually becomes so this kind of picture, here is the graph of function. I will explain what that means by using the MATLAB. So let's say I'm taking a point in this set. Let's say it looks like a surface. It's actually a surface. So what I mean by this point, it has three coordinates, x and y and z. So x, y, and z coordinates are here, and the condition that this point satisfies is that x, y must lies in the domain D, and z is equals to the value of function when xy at xy. Okay, so I'm collecting all this kind of point. So basically similar to drawing a line or drawing a region in this xy plane, but we are doing on this three-dimensional space. So normally I teach you how to draw by hand this kind of graph of two-dimensional function, but I will give you how to draw in the MATLAB because it's more convenient and more powerful than drawing it by hand. So let's look at here. Let's look at this one. That we're going to explain that later. All right, so drawing a graph of two variable function. So for example, let's start from z equals to x squared minus y squared. So first of all, let's define two variable functions. So I'm going to name it as f, and there are two independent variable x, y, so I put it here, and then it spits the number z given by x squared minus y squared. So instead of taking hat, I'm taking dot hat here. So the reason why I put dot is that I could put x and y as an array of numbers instead of just one numbers. So if I take x and y as an array of numbers, dot means that it operates this hat, which is the power, on each entries of this array. Okay. So if I don't put the dot here and I put x and y as an array, then I'm taking this MATLAB tries to do the matrix square So it simply tries to multiply matrix X with matrix X. But if the size of this array is not correct, then this makes a problem. So I'm putting dot here. And the second thing I need to do is that I need to make a grid on this domain of F. So I'm using mesh grid and linspace of -1 to 1. So it means, usually the mesh grid needs another linspace for y coordinates, but this is the correct method. But if I have the same axis, same array for x and y grid, then I can simply abbreviate that into one linspace here. So this command means that take a array from -1 to 1 divided by 99 intervals, consists of 100 entries, and then splits your area -1, 1 cross -1, 1 into these 99 times 99 rectangles or squares. So, and then the rest of the thing is the surf f x y. So surf gives the graph of surface. It needs the mesh grid of x and y, and then corresponding z grid axis. Okay. So if I draw this, I get this picture. I can even rotate this. So you see, this is like a saddle on a horse, so it's called a saddle. Okay. Now, the way the MATLAB graphs the surface, or almost any other program draws, how any other program draws this kind of picture, is to mesh grid your domain and then draw lots of planes, flat planes. What I mean by that is, if I take a coarse this array, in the first picture I draw it like 100 entries array, but if I take 10 entries array, then my picture looks like polygon. So each tile is simply a plane, flat plane, and I'm taking all the sets of flat planes and taking into and put it on side by side, and makes it looks like a curved surface, but it really is not. Okay, it just looks like curved, but it's actually a set of flat planes. The same thing for when you draw a curved line. So when you draw a curved line in the MATLAB or any other programming, it simply draws a set of short straight lines, and in our eyes it looks like curve if the short length and the length of each segment is very small. So that's how we draw the graph of surface, and that's the case for two variable function. What if we have this parametric function f of t equals to t squared t cube? So in that case, let's define our function to be just this function. But now remember that there is no way you can define a tuple of numbers. It's actually a vector of vectors of numbers. Okay, so I draw this, and also I need a domain of t. So I want to range my t to be -1 to 1. Okay, and let's draw it. Now this is not a surface. The graph of this kind of parametric function is not a surface. It's a curve in two-dimensional plane. So what I have to do is to draw a plot. Okay, 2D plot actually. And first of all, I need to draw the x coordinate and y coordinate of ft, right? So let's say ft of 1, I'm not sure that it works, ft of 2, yeah, it doesn't work. So actually I need ft to be the first coordinate, ft of 2, yeah, it doesn't work. So I need to define this x and y coordinates separately, t square and yt t cube. So I'm plotting this x and y similar to plotting the epicycles in previous slide. What's wrong here? Oh, so sorry. So it's x, not y. Okay. So xt and yt. So this is the picture. Let me put x is equal here. So it's pointy points here on 0, 0. If you want to know where is when t equals -1 and where is t equals 1, you can simply plug in your numbers of t into the coordinate x and y, or as I showed before beginning our class, you can draw an animation. And you're plotting a point from 1 to I, and draw now, let's see, axis from minus 0.5 to 1.5, minus 1 to 1, and axis equal. So this is the basic way to make an animation in MATLAB. So what's wrong here? 11. Okay, I need one more parenthesis and one more parenthesis here. 1 to I, 1 to I. Okay. T from, oh, I'm sorry, so this is I, not T. Okay. And then you see there is an animation of a line making progress on up to 0, 0, and then from 0, 0 it changes direction and it moves to upward again. So it starts from the bottom here. So bottom is when t equals 1. When t equals 1, the t value, the array of t, contains -1 when t equals 1, I equals 1. So the bottom is when t equals -1, and top is the t equals 1. And you can draw, okay, so let's do this. So this is different thing. So we have another equation that ct equals to cosine t and t sine t. So basically this is a spiral, but this is a parametric curve in 3-dimensional space. So I need 3 coordinate function, xt and yt and zt. And let's take t from length space from 0 to, let's say, 6 pi. Now I need to draw a line in 3-dimensional space. So instead of plot, I used plot 3. So basic plot is for 2-dimensional plot. Plot 3 is for 3-dimensional plot. But this is different from surf method. Okay, surf is drawing a surface. Plot 3 draws the line. Okay, line in 3-dimensional space. So xt, yt, and zt. So this is the picture. So it's like spiral. So it's spiral. It rotates the x and z axis, but it moves toward y direction, right? It's like a spring. So if you have any question, stop me anytime. I can re-explain this. or we can go back to our slide. So we draw this graph. I hope you do this again. And now these examples of graph is for two variable function or parametric function of in two-dimensional space or three-dimensional space. But let's say we have three variable function. W is the independent variable, and x, y, z, including z, are all independent variable. How can we draw this kind of function? In that case, we're going to use a level set. Okay. So level set is a set of points x, y, z in three-dimensional space such that it is a collection of points where value of function equals to c. Okay. Normally, if you really want to draw the graph of four-dimensional of three variable function, you need four-dimensional space, because if you have three variable function, then graph of this function is x, y, z, w, where w is f, y, z, and this requires fourth axis. So we need to draw in four-dimensional space, but there's no way we can visualize this four-dimensional space in any program. The only way we can do this is try to draw this level set in three-dimensional space and then see how does this level set changes by changing the value c. So for example, if you want to draw a level set of this three variable function, these are the example of pictures when c equals to -1, 0, and 1. So for example, let's say c equals to -1. That means I want to draw a set of points satisfying x plus y square minus z square equals to -1. Right? So if I rewrite this, this is xy square equals to z square minus 1. So on the left hand side here, it's always positive. This guy is always positive. However, right hand side could be negative if z lies between -1 to 1, but that cannot be happen unless you're talking about the complex number, but we are always talking about the real number system. So you cannot have z from -1 to 1. So z must be either bigger or equal to 1, or z is less than -1 or equal to -1. So when it happens, when z is bigger than 1, then you have the upper side, z equals to bigger than 1, then you have upper side leave here, and x plus y square equals to some value. If you take the section perpendicular to z-axis, you always get a circle, right? So you have an oval above this z equals to 1 plane, right? And this is when we have z is less than -1 or equal to -1. So same thing for other pictures. So this is when z equals to 0, and this is c equals to 0, and this is when c equals to 1. Okay. Now, this is the important thing. So let's say we have a vector space V, and we have an open subset of Rn. So we're going to define what's called the vector field here, and it sends the point to a vector. So the domain is the subset of Rn. So Rn is just the space of points. Okay, and V is a vector space. So this F can be written as x to V. So x is a point and V is a vector. And we already saw the vector field in last semester when we talking about how the solution curve of this differential equation moves, we draw the vector fields, directional fields actually, on the plane, and then try to imagine how the curve looks like. So it's similar to that. So directional field is putting an arrow at every point to the same direction of the slope of a function. So if you're taking an arrow in two-dimensional plane as a vector, then this vector field is just a generalization of this direction field. So you can take a vector field on any dimensional space to any vector space. And then we were going to see the example of vector field going back to the first slide. Before we do that, let's talk about the linear transformation first. So the vector field is sending a point to vectors. Linear transformation sends vector to vector. Okay. So this function f is sending a vector in v to another vector in w. So v and w, the large V and large W, are vector spaces. And if you want to call this function as a linear transformation, you need two conditions. The first condition is that this function preserves the, so this is t actually, not f. This function preserves the vector sum. Okay, so if you take the sum of two vectors before you take the value of this vector transformation, it's the same thing as you take the vector sum after you take the vector, the value of transformation of each vectors. And second condition is that it preserves the scalar multiplication. So it means that you can either multiply your scalar number before or after you take the value of transformation, and the results are the same. So important thing about linear transformation is that you can always represent linear transformation by a matrix, and matrix multiplication represents the composition of linear transformation. Here I'll give you an example. So let's say I'm going to define t to be xy is sends to x plus 2y and 2x. Okay, so I'm going to rewrite these vectors as x, y, and this as x plus 2y and 2x, because this is a linear transformation. So you can check why this function is linear transformation by yourself, checking these two conditions. I'm going to represent t by 1, 2, 2, 0. Because, so if I replace t by this 2 by 2 matrix, then I can simply rewrite this equation as 1, 2, 2, 0 matrix multiplication with xy is equals to. So if you remember the rule of multiplication of matrices, 1, 2 times xy gives x plus 2y, and 2, 0 times xy gives 2x, right? So this equation, the definition of linear transformation of t, is exactly same as writing your matrix multiplication. So you can identify your linear transformation t by this 2 by 2 matrix. And let's see another example. So let's say S is sending your uv to u plus v. Okay, Now, UV, it can be written as two-dimensional vectors, UV. And this UV is a scalar number, but you can also represent this as a one-dimensional vector, so it's U plus V. So by the same method, you can represent your S as 1-1 matrix like this, because you can rewrite this definition of S in matrix multiplication 1-1 times UV, and if you multiply these two matrices, you have only one entry, 1-by-1 matrix, U plus 1, U plus V, sorry. Now I want to composite these two functions. So only way I can composite this is that I composite T with S, because T is a linear transformation sending two-dimensional vector space to two-dimensional vector space, and S is sending two-dimensional vector space to one-dimensional vector space. So S composite T sends two-dimensional to two-dimensional and then one-dimensional, right? And let's try to composite this function by hand, because we have a specific definition of this. So I'm taking ST of xy. So first I'm taking txy, which is x plus 2y to x, and then I'm taking definition of S, which is 3x plus 2y. Okay, so that's the function S composite T. Now let's take a matrix multiplication. So S and T are represented by 2-by-2 matrix and 1-by-2 matrix. So ST should be represented by 1-1 and times 1-2, 2-0. So if you multiply these two matrices, you get 3 and 2. So normally you don't put a comma in this matrix here. So what I mean by that is I represent my S composite T linear transformation as 3-2 matrix, 2-by-1 matrix, 1-by-2 matrix. So let's see whether it matches our result in the previous computation. So when I take ST with xy, I can rewrite this as 3-2 times xy vector. That gives 3x plus 2y, right? So they are the same. So these guys are the same, right? So we explained the meaning of matrix by matrix multiplication in the previous lecture, saying that if you have a matrix meaning the column and row has special meanings, then matrix multiplication could mean something. But there's a bigger implication of matrix multiplication. If you have a linear transformation, your matrix each linear transformation represents some matrices, represented by some matrices, and multiplication of those matrices are the matrix which represent the composition of two linear transformation. So this is an example. You can actually prove this in general, but we don't need that. So we were going back to our first page. So here I want to explain a vector field, but also very important concept which appears in physics. The coordinate systems are not only the Cartesian coordinates. There are other coordinate systems. You might know polar coordinate system, learned in the previous semester. That represent another coordinate system in two-dimensional space, namely if you have Cartesian coordinates x, y, then there are other ways to locate your point. by taking the length between the origin 0 and the point x comma y, and taking the angle between positive x-axis to this this line, one-way line from origin to the point x comma y, right? And taking the angle from counterclockwise direction. So if you want to convert one coordinate system to another, there's a way you can do this, is that x squared plus y squared and square root of that is r, okay, and then tangent theta is y over x, and if y is 0, so x over y, y over x, it's y over x, but I wrote other way. Okay, if x is 0, then you can use your inverse cosine or something. The important thing is I want to point out another vector instead of our x hat, which you represent by E1, the unit normal vector, and y hat, which is E2, unit normal vector. There are another vector, r hat or r theta. Usually it also written as r hat, or this is called theta hat here. So these are the vectors which represent the direction where r changes but theta doesn't change, and theta changes but r doesn't change. So think about r hat. I want to be a unit vector which points to the direction where r changes but not theta. So in the two-dimensional picture, if I had a point x comma y here, then this direction is r. So if you don't want theta to be changed, then you have to go to this direction, right? This is the r direction. So r is moving toward the direction of the position vector OP, but I want the normal vector, so I need to divide that OP vector by its norm. Okay, so OP vector is simply x comma y. So I have to take the norm of OP as square root of x squared plus y squared. So that's how I get the r hat. How about the theta hat? So theta hat is the point, a direction where you change the theta but not r. So basically you're moving around the circle of radius r. So here's r, the circle of radius r, and I want this direction, which is perpendicular to the radius direction of the circle. So this is theta hat. Now how do we get the theta hat? So easy way is to get theta by looking at the actual theta value. I want to express the theta hat using r and theta. So theta hat is direction of r. So this is r cosine of 2 pi plus theta, r sine 2 pi plus theta, because if you keep looking this ones, so this is theta and I'm adding 2 pi again, right? So that's our new theta, which is the angle between the theta hat and the positive x direction. And if I compute this, so this is r of what? Cosine, so it's minus sine theta, and this is cosine theta. So again, I mentioned that the theta hat must be normal vector, so this has a norm r, so I need to I divide by r, so I get rid of this r. But before we do that, I want to express this r and theta in terms of x and y. Okay, so I must replace this r theta and r cosine as y and x, and r is simply in the length of OP vector, so divide by x squared plus y squared. That's how we get theta hat. So these r hat and theta hat are example of vector fields. This r hat and theta hat sends a point to two-dimensional vector. So the domain is space of points and the range is two-dimensional vector space. So as I said, I'm going to write R2 as also two-dimensional Euclidean vector space. And these are examples are vector fields. Okay. Again, let's keep moving on three-dimensional coordinate system. So there are two coordinate system famous ones. One is the cylindrical coordinate system, the other is spherical coordinate system. So cylindrical coordinate system tries to divide your three-dimensional space into shells of cylinders. So every point can be considered as a point lying on some cylinder of radius r. So let's say this is r, and let's say I'm putting a point here. Okay, so when I have a point, it must have a height of the cylinder based from xy plane, so that's z. So this z is actually equals to the z in Cartesian coordinates, so we got the same z here, and x and y coordinate are actually come from the polar coordinate system, so it's nothing but polar coordinate system, but we have also another axis, z axis, so that's easy. How about the spherical coordinate system? So idea is that you want to put a point on the sphere of radius r. So let's put a sphere here, and let's say the sphere has radius r, and let's say we have point here. So to find out xyz coordinate, or other way from xyz coordinate, I need a three variable which measures the radius r, which is r here. So let me enlarge this. Radius r, and also if I take a projection of this point on xy plane, these are x and y, I need the angle between this positive axis and this line, and also I need the angle between z-axis and the line from the origin to the point. Okay, so these are x, y, z, and I need r, theta, and phi. Watch for the role of this variable theta and phi. In physics, they switch the role. In physics, they use theta to be the angle between z-axis and this line segment, but in mathematics, I think in mathematics they use theta for this angle, just to consistent with this polar coordinate system theta. Sorry. Okay. I'll use this here. Okay. So in cylindrical coordinate system, we also have a way to express our vector r and theta. Basically, before we do that, the vector z is same as the k vector, which is e3 vector, and the others are exactly the same, except that we have other the extra coordinate because these are three-dimensional vectors. So all these vectors are vector fields. Okay. Important thing is these ones. I want to express my row. Sorry. So usually row writes row here instead of r. Okay. So here we have rho as the radius of this sphere. Rho direction and phi direction and theta direction. So theta direction is the same as polar coordinates, as you can imagine. So these are the same. And rho direction are also similar to the r direction of polar coordinate system or cylindrical coordinate system because it's simply direction of OP vector. So let's see, this is OP. Let's change the color, please. OP divided by OP norm. Okay. So denominator is the norm of OP and XYZ is the OP vector. How do you get the psi? I mean not psi. What was the phi? How do you get the phi vector here? So what is phi vector? Let's look at the picture of sphere again. So r vector, let's see here. So theta vector is this direction. So you have point right here. So and you have a circle, a trajectory of a point where theta changes, but not rho or phi. It's not phi actually. So actually this is psi. It's not psi. What was the? Yeah, phi. Yeah, phi here. So that's the theta hat. Okay. How about rho? Rho is this guy. Okay. So rho is this guy. So phi vector. So you have a phi vector where you're changing your phi angle, then you're moving to this trajectory so that you get this is your phi vector. Sorry, I used the other symbol here. So this is phi. This is phi. Okay. So we have three vectors. This one, and this one. It looks like it's not a right angle. Actually, it is a right angle. If you think about a sphere and then you're moving on to the phi directions, and it's always perpendicular to the rho direction. Okay, so these are perpendicular. Rho phi and theta phi are perpendicular. And how about phi? Phi is perpendicular to rho, and it's also perpendicular to theta. You have to imagine it geometrically. So put sphere in your mind, and then try to imagine how phi looks like, phi direction looks like, how rho direction looks like, and then confirm that these two vectors, rho and phi, are perpendicular, and now tries to look at how the phi direction look like. So how we get this phi is by taking the direction where perpendicular to both rho and theta, right? So only way you can do that, easy way you can do that, is by taking a cross product. So direction, the order is important, otherwise you get the negative direction. So order of getting the right phi direction is that you take theta first and then rho next. That way you can get the correct direction of phi by the right hand rule. So now in the previous here we have both the formula of phi and rho. So then this is given by theta cross row divide by the norm of that vector. Okay, that's how we get this. And these three vectors are actually a vector field. It changes by the point of x, point of p, coordinate of p. Okay. And this is actually a remark. You don't need this one right now. But as I mentioned about four-dimensional space, when you want to draw the graph of three-dimensional function, you need four-dimensional space. And you might wonder, instead of Cartesian coordinate, is there another coordinate system in higher dimensional space? And there is, which is called a hyperspherical coordinate. Also, it's called simply called the spherical coordinate system. It simply generalized the spherical coordinate system in three-dimensional space. So instead of taking one phi, I get n minus 2 phi for this n-dimensional space. So in that case, you have rho phi 1 to phi n minus 2 to theta to represent the Cartesian coordinate of n-dimensional space from x1 to xn. So what's good about this? There are systems that is easily explained by the spherical coordinate system instead of Cartesian coordinate system. So that's all reason. All right. Okay. So if you have any question, please ask anytime. If you want to go back to some slide, it's okay. I can explain that again. So far, so we talked about graph of function and vector fields and some n-dimensional space stuff. Now, all these are for explaining the characteristic of multivariable function, and we're not still yet. Until now, we're going to explain about real nature of multivariable function from the basic definition of calculus. So let's talk about two-dimensional function, two-variable function, sorry, because that's the most simplest multivariable function you can think of. And suppose that this function is defined on the entire two-dimensional plane. We're going to call the constant L as a limit of this function at the point x0, y0 if it satisfies the following condition. It says that if we pick any or arbitrarily small epsilon, there exists also a small delta such that whenever we have a distance between x, y to x0, y0 less than delta, then this inequality always holds. So I will explain geometrically what this means. This is actually definition from analysis, another subject of mathematics. In most of calculus, the textbook, they don't talk about this definition. They simply saying that if xy is close to x0, y0, then fxy is close to L. They just use this as a definition of limit. But what really means is that the following. So we have x, y, and z coordinate, and here is my x0, y0, and here's some random point x comma y. Now, so intuitively what this code means is that if I try to move my x comma y near to x0 comma y0, then there is a graph of function. So this is the graph of function of z equals to fxy, and there are points corresponding to this x comma y and x0 comma y0. Let's say xy fxy. Let's move this picture here. Okay. xy, and here we have a point x0, y0, fx0, y0, right? So if xy moves towards x0, y0, then these points on the surface, on the graph of function, also moves towards the desired points here, right? So when it does, then we're only looking at the coordinate of z axis. So z coordinates f, x, y, and fxy is here. So this is fxy, and let's say this is fx0, y0, supposing that this is z-axis. Okay, so if you're looking at the value of z coordinates, then it simply moves towards this new the z coordinates of at x0, y0. So this quote says this picture. Okay, but what we need rigorously prove is that whenever we have a point lying sufficiently close to the desired point, let's say I want to put a ball around this desired point x0 and y0, and whenever we have a point xy lying inside of this ball, then I want to guarantee that my value of function lies in the near neighborhood of fx0, y0. Okay, so when I say the distance between these 2 points is less than delta, that means xy is in the ball of radius delta centered at x0 and y0. So then I want that this one, which says that fxy lies inside of L minus epsilon to L plus epsilon. Okay. That's a good question. So the question is why we explain that in three-dimensional space where this f of f is defined on two-dimensional space. So reason why is that, first easy way is that this function contains 3 variables instead of 2 variables. So among 3, 2 are independent, 1 are dependent variable. So we have x, y, z. X, y are independent variable, and z is a dependent variable. When we talk about this function, we have to think about this 3 variable at the same time. We cannot separate out z coordinate when we talk about this function because value of function is z. So in order to explain this 3 coordinate in the same time, we need 3-dimensional space. Another complicated explanation is that when we talk about this function geometrically, we need a graph of function, and this graph of function lies inside of three-dimensional space. So we need a three-dimensional space. So ideally, when we study a function, okay, when we study about the function, we cannot study this function only by looking at the independent variable. We need an output. We need to consider the input and output of function. Okay, so that's why we considered our graph of function of single variable function in two-dimensional plane, right? So by looking at the graph of single variable function, we understand how function looks like. So same thing for two-dimensional space, two variable function. When we're talking about two variable function and study about two variable function, we need three-dimensional space. We always work with the three-dimensional space, either talking about the graph of function or think about this concepts of limit. Okay, you can think about this function in two-dimensional space if you really insist that, let's say this is our domain, okay, of function, and let's say this is our range of function, the one-dimensional space. Okay, so this D is R square. So you can explain this as x, y approaching to x0, y0 in R2, then corresponding point where fxy and fx0, y0 is fxy approaching to fxy, fx0, y0. So there's a way to explain that in two-dimensional plane, but in this way, in this picture, you also need an extra axis here, right? So if you combine these two, just give us three-dimensional space. Right, so the function defined on R1 is called a single variable function, but you have to be careful that there's a parametric function which also defined on R1, but it has a multi-dependent variable, right? So that's also called a multivariable function. So if you have a function from R1 to R1, that's a single variable function. But if you have a function from Rn to Rm, if n is bigger than 1 or m is bigger than 1, then this is called a multivariable function. Okay, so even the parametric function is defined on one-dimensional space, but it has two or more dependent variables, so we don't call that as a single variable function. It's a multivariable function. But if you separate out the coordinate function of parametric function, they are a single variable function. Okay, okay, all right. Okay, so we have some time here. So once we know about the concepts of limit, we're now ready to talk about the continuity of a function. So similar to the continuity of single variable function, but we're talking about the two variable function. So basically, if the limit of function at x0, y0 is same as value of function, then we call a function a continuous function. So there's a big difference when we talk about this limit. Okay, so it looks same because when you're talking about the single variable function, the continuity of single variable function, we just simply said when x goes to x0, then fx goes to x0. That's the continuity definition of single variable function. So what's the difference? The difference is when you check the continuity of a single variable function. For example, if you have a graph of function looks like this, and you want to check whether this graph function is continuous at x0, you only need to check two directions. One direction is from the positive side of the x0. The other one is from the negative side, or left hand side. There are only two directions to check. You'll need to check that when x approaches to the right hand side of x0, that function value goes to f of x0, and when x goes from the left hand side of x0, the function value approaches to f of x0. But when you're talking about the two variable function, you need to talk about entire direction to x0, y0. So it says when, so this thing is somewhat ambiguous. So I want to approach my point xy to x0, y0. You can approach your point anywhere. There are infinite directions, right? Because you can take any xy you can take any starting point. And also, not only the direction matters, the path also matters. The trajectory of approaching curve also matters. You can approach to your point. Approaching to your point by straight line, but also you can approach to the point in this curvy line or weird line like this one. So there are infinite direction, infinite path trajectories. So there's no way you can check by simply looking at the graph, or simply by checking some few example of path of approaching xy to x0, y0 to check that this function is continuous in the two variable function. Here's an example. Maybe I give non-example first. Okay. So, yes. So if you want to prove a continuity of a function, you need to go back to the definition of the limit. Okay. However, if you want to disprove the continuity of a function, then you have to show there is a trajectory which where this equality fails. Okay, so I'm going to show the non-example first. So proposition first of our proposition is that this function is not continuous if there is a path which converges to x0, y0, but this value, this one variable function f composite c, does not converge to fx0, y0. So let's look at this one. So I want to prove that this function defined as this follows. So whenever x, y are not zeroables, then this ratio is well defined. But when x, y are both 0, it's not defined because denominator is 0. So we define the value of function to be 0 forcefully. So we want to show that this is not continuous at 0, 0. So let's try to get some path which approach to 0, 0, but the value of function does not approach to 0. Find a path or parametric function ct where converge to x0, y 0, 0 when t goes to 0, such that f composite ct does not converge to 0. So you can start from the straight line, okay? Let's say I want to start from, let me just give a new page here, another page. So take one. Let's say I want to take t, t, okay? So here's a question, sorry, I missed it. Yeah, so the question is, can we think about the limit as taking a limit of projection onto xy plane? Well, actually it's opposite. So we have a graph of function. So when we think about the limit of function, you start from xy plane, okay, instead of taking projection. So we're starting from the domain, and then I want to find out where the value of function approaches when xy approaches to x0, y0. So I'm going to take an inverse of projection here. So this is xy, fxy, and I want to see where this point moves when this xy moves in xy plane, okay? So take a limit of xy when xy goes to x0, y0, okay? So it will stop at some point. So let's say this is x, y, and L. So xy coordinate will always, xy coordinate is always be x0, y0, and it will go to some point. If it goes to some point, it will have a z coordinate called L. So if it stops at x0, y0, L, then L is the limit of fx0 at x0, y0, okay? So actually it's opposite. So if you want the continuity, definition of continuity, you simply assert that this L, the x0, y0, L, is the inverse projection of the point x0, y0 onto the surface of graph of the surface graph, graph surface of the function f. So good question, thank you for asking. And okay, so go back to our function example. Let's try this trajectory. So basically it's approaching to 0, 0 on 45-degree angle, so t, t. So let's try to take the composite fc. Then this becomes 0 or t 4 t square divided by 3t square, right? So if I take the square out, then this square out and this 2, right? So basically this is equals to 3 t square minus 4. So I can do this. I can get rid of t square because the first formula is only when t is not equals to 0. So denominator is not 0. So I can divide my t square on both sides. So I get this. So when I take the limit when t goes to 0 of fct, I get t squared goes to 0, it goes minus 4 over 3. That's not equals to value of function at 0, 0, which is 0. It's previously defined here, right? So I done with the take 1, but sometimes your choice of trajectory doesn't work to prove the discontinuity of functions, so then you have to take another path. So choosing path is just the work of art, so you have to find a right path to disprove the continuity. So but we done this for one take. So this is not continuous function. Let's try to look at how it look like. So let me give you a picture of this surface. Let's draw this here. So everything is composed of a formula called xy is x4 minus 4 times y squared, and then divide by x squared plus 2 times y squared. I forgot dot here, dot. And then do the same what I did in the previous example, mesh grid. Let's say I want to plot this around 0, 0, so minus 1 to 1. Okay. And then surf xy and fxy. So this is the graph. This is how it looks like. So you see this something going bad at 0, 0, right? So it's like, it looks like it's not connected here. Actually, it's not continuous, but it's a limitation of our program. It simply cannot draw it. If you make it bigger, make it finer, like say I want to put 500 points instead of 100, okay, then this gap, this this valley get narrower, but it actually goes to almost, it touches to each other. Okay, so in this picture it says that the limit can be anything between here to here, right? So if depending on which direction that you're approaching. So for example, let's try to draw the direction that we draw that we found in the example here. So let's see, I want to take the length space of minus 1 to 0, and I want to draw a trajectory of t, t, and plot 3 of xt, yt, and actually I don't need this, right? Just t. So just tt and ftt. Okay. So I want to plot this as red and line width as 2, so that it makes clear. And hold on. So here's the line. So if you project that on the xy plane, it's a 45-degree angle straight line on xy plane to origin, but I plot it on the surface by taking an inverse projection here. So it approaches along this curve, so it goes here, right? What if I take another path? So what if I take t, 2t instead of t, t? So t, 2t, f of t, 2t. let's say I want to draw it by blue, line width 2. So let me give x is equal. So if I look at these ones, so the red one is t comma t direction. It approaches to -4/3. When I approach to t comma 2t, it approaches to another direction, another point, somewhere below than -4/3. So let's try to compute what this limit is. So for example, if I take ct equals to t comma 2t, then fct is x squared t fourth minus 4 times y squared, which is 4t squared divided by x squared plus 2 times 4t squared, which is 9t squared t fourth minus 16t squared. So if you divide that, then you get t squared minus 16/9, then 0, right? So when t goes to 0, f's composite ct becomes -16/9. So in the blue line in the MATLAB we saw before, that's -16/9. So the limit depends, so let's look at this picture. The limit depends on the path you choose which approaches to point. Then it's not continuous. And if you draw the function of graph of function, it looks obviously discontinuous at that point. So it's not like you have a hole in the surface of graph. Sometimes you might have a hole in the picture of in the surface, and that's obviously discontinuous. But if you think, it's unlike the graph of single variable function. So when you have single variable functions, it says even if your function is sharp at point, as long as it's not breaking, then it's continuous. That's the case for single variable function. But when you have two or more variable function, then continuity says that you have to look at the path which approaches to the point, and if the limit is different for each path, or it doesn't approaches to the value of function at that point, then it's discontinuous. And the graph may not look like a punctured surface. Okay, it's something like a very weird behavior. Right, so let's take this example and then finish our today lecture. So we want to prove that this function is continuous at 0. So what we need to show is that the limit of xy goes to 0, 0 of xy is 0, because that's the value of f00. But when xy is not 0, 0, then the formula of fxy is xy over square root of x squared plus y squared. And therefore what we really want is this. Okay, I want this fraction goes to 0 when xy goes to 0. So here is the rigorous proof. I don't expect you to understand fully how to prove this kind of limit, but at least you have to see once in your lifetime how this epsilon delta proof works. So let's say I want to take a random epsilon, which is positive. We assume to be very small positive number, but doesn't have to be actually small, because small is an ambiguous word. So epsilon is arbitrary number. So we want to find delta such that if the length between xy and 0, 0, which is simply x squared y squared, is less than delta, then the value of function xy divided by x squared y squared minus the value 0 is less than epsilon. So we want to find such delta. Okay, let me put you here. All right. So let's say so let me think about this one first. So when you have x squared y squared divided by 2, it's always bigger than or equal to what? X, y. So this is a geometric equation. Can you see this one? Yes. Okay. So geometric inequality here. So therefore, squared here. So we have xy. So right, so we have x squared y squared over xy is always less than or equal to square root of x squared y squared, right? Now what we want is that this one, I want this inequality to be true, right? So I want, if this is less than epsilon, then everything is fine. So let delta to be equal to epsilon. Then what happens? This x squared y squared over 2 is less than delta over 2, and this is equals to epsilon over 2, therefore it's less than epsilon. Therefore what we have here is, because of this formula, xy over square root x squared y squared is less than or equal to 2 over x squared y squared, which is less than epsilon, and we are done, because this equation is exactly the same equation that we want in the beginning. So we already found that there is a delta which satisfies this condition, that if the xy, the length of xy and 0, 0 is less than delta, then the equality hold. So we prove that the 0 is the limit of this function, and also 0 is the value of function at 0, 0, so there f is continuous. Therefore fxy is continuous. Okay. So let's try to draw the graph of function, this function, this one. So f is xy and x dot y divided by square root x squared y squared, and xy mesh grid then space -1 and surf xy fxy. So there is a highlight here, so something could be wrong. It disappeared. It's okay. So this is the picture. So you see, this formula is not defined when x and y are both 0. However, we defined that to be 0, but we didn't mention this in the code because it's useless to, there's no meaning to find one value of function in the graphing the function. However, what happens at 0, 0, it has a sharp point, right? There's a pointy parts of this picture at 0, 0. So, however, it's not like the discontinuous picture. It doesn't have a hole, it doesn't have a valley, like the steep line. It connects at 0, 0, but it's not smooth. But so what's the difference between this kind of picture and the saddle point, like really smooth curve, a smooth surface? The difference between this pointy surface and smooth surface is that when you take a differential of two variable function, this one is not continuous when you take a differential of functions. But if you have a smooth surface, you can take a differential anywhere. Okay, so one more question. So in a single variable function, we assume that x is less than delta, but in two variable function, we assume that the distance between the origin and xy is less than delta. So you're actually just taking, you're saying the same thing. So reason why I take this one is that, sorry, so I changed the slide. So I think we were asking about this part. So here, so I used this this one. So where this inequality square root of x squared plus y squared less than delta comes from, because we're talking about the distance between the point xy to 0, 0, and the definition of distance by Pythagoras theorem is that the square root of x squared plus y squared. Okay. So what you're saying is right. So we are assuming that the distance between x and y and 0, 0 is less than delta, is the assumption of the epsilon delta definition of limit or the continuity. I think that answers your questions. Right, so yeah, not only for this question, but in general, we are taking this kind of, this is just a definition of distance, right? So reason why I take the square root of x squared plus y squared is that because I'm taking a distance between the point and the origin, okay? So if it's not the origin, then I should take x minus x dot 0 square. So let me rewrite that. So we have this distance between xy and x0, y0 is square root of x minus x0 and y minus y0. So luckily we had a formula of distance aim as denominator of the formula of a function, but sometimes we may not have the luck, so we have to work with this inequality where x0 or y0 stays inside of the formula, and somehow we have to pull out the desired inequality about epsilon. So so basically what you're saying is right. We are doing this way in general in two-dimensional two variable function. Okay, so thank you for asking. And so far we talked about graph of function, continuity of functions, and the next thing we have to talk about is the differentiability of function. So there are several definitions of differentiability of a function, because we're not looking at the single variable function. So we have a infinite direction of taking differentials, or you can also define the differential in totally different concept. I will explain that the next time. So if you have any question, please ask anytime in any ways, and I hope to see you next time. We're not going to have a MATLAB special separate session because we already done many MATLAB exercise. So see you on Friday.